All right, we're here to talk about rational expressions. We have two rational expressions in front of us right now. I first want to talk about simplifying rational expressions. This first expression here you should have seen previously when being introduced to the rules of exponents. This is the type of rational expression we're actually really interested in this section right now. The biggest difference between these two rational expressions is the first one, the only operation involved in the numerator and the denominator is multiplication. In this expression on the right, we have addition and subtraction going on. It creates a significant issue or a significantly different method for attacking this kind of expression. I'm going to quickly just discuss how to simplify an expression like this. It's all about the fundamental principle of fractions. We're just canceling common factors. I won't show all the little details for that, but I'll show you how I go about doing it. In this expression right here, I'm going to cancel a common factor of 4 between these coefficients. So I cancel a common factor of 4, and I'm left with a 3 here and a 4 down here. Now when it comes to the variable expressions, I'm not going to actually directly apply the rules of exponents. I'm just going to cancel common factors. Again, this x to the 8th is 8 factors of x being compressed together into this exponential notation, and the same thing with the x to the 4. What I'm going to do is cancel 4 x's from both the numerator and the denominator. So if I cancel these factors, up here I'm going to get an x to the 4th because I've taken away 4 of those x's. I'm going to take away all of these 4 x's down here, and I always am left with just a 1, a factor of 1. The same thing with the y's. I'm going to cancel 3 y's from each of these. That leaves me with just a 1 here. Not 1 y, just the number 1, because all of the y's have canceled. And then I have a y squared right here. Then all I need to do is I'm going to multiply the results of all that canceling together. So up in the numerator here, what I have is 3x to the 4th, and in the denominator, I have a 4y squared. Okay, and again, that's a foundational piece for the conversations we're going to be having today. But the main issue we have, as said before, is that we have additions or subtractions involved here. We're not allowed to cancel things that are being added or subtracted in the numerator and denominator. We're only allowed to cancel factors. The fundamental principle of fractions, which are our guiding concept here, is we have to cancel things that are multiplied to the whole numerator or whole denominator. We do that by factoring. So what I'm going to do now is completely factor the numerator and completely factor the denominator. So I'll show those steps right here. When I factor that numerator, I'm going to get to x plus 7 times x minus 1. In the denominator, I'm going to factor that into an x plus 7 times an x plus 8. Now that I've rewritten both the numerator and denominator in terms of multiplication, and I have 2 factors in each, I'm now allowed to cancel the same way that I was canceling over here. What I would do in this case is cancel these factors of x plus 7, leaving me with the final expression of x minus 1 over x plus 8. Again, really important is that you might be thinking, hey, why couldn't I cancel these x squareds in the beginning? And the reasoning is because the x squared is being added to the other stuff in the expressions in the numerator and the denominator. You're not allowed to cancel things that are being added or subtracted. You're only allowed to cancel factors in the numerator and denominator, as I did with the x plus 7. And the same thing with this final expression. I can't cancel the x's or anything else because nothing is being multiplied, or nothing that's the same is being multiplied to the numerator and denominator. Let's now look at multiplication of rational expressions. All right, here we have 2 rational expressions that we're multiplying together. One thing I want to remind you and emphasize is a rational expression is simply a fraction with an algebraic expression in the numerator and or denominator. So we have these 2 expressions. The key is we treat them as fractions always. We just need to make sure we translate all the concepts we knew from fractions into the rational expressions. So first, we're going to be asked to multiply and simplify these 2 expressions together. Now, while we could do it in that same order, things get gnarly pretty fast. The fact is, we would multiply straight across, just like we do when we're multiplying fractions. If we multiplied straight across, There's going to be a lot of terms and things are going to be very difficult. And importantly, when it comes to simplify, we're going to have a heck of a time given all the expressions and the order of the polynomial that we're going to have. The same thing in the denominator. The trick that we're going to employ is cross-canceling before we multiply, just like we do with normal fractions. And I just want to remind you of this right here. While we could multiply straight across and then simplify the common factors, the trick is you can save yourself a lot of time and heartache if you cancel between the numerator and denominators first. That example would be like, for instance, before I multiply, I'm going to cancel a common factor of 5 between this numerator and this denominator, getting a 5 here and getting a 3 here. And then with the 8 and the 24, I can cancel the common factor of 8 between those. So 8 goes into 24 3 times, and 8 goes into 8 1 time. Now that I've canceled those common factors, then I can multiply across. And the beauty of this move is that I end up with, after I multiply, a completely simplified expression as long as I've canceled all the common factors before I multiplied. We're going to apply that same strategy here. As always with rational expressions, when we're doing anything with them, the first thing we're going to do is we're going to factor everything that we can. We factor so that we can use the logic of fractions and these multiplicative structures of fractions. So I'm going to go through all of this, factoring the numerators and denominators of both of these. This first one, this is a difference of squares. This factors into x plus 3 times x minus 3. Right here, I'm just looking for two numbers that multiply to be 15 and add to 8. Those two numbers are a positive 3 and a positive 5. Going on to the second rational expression here, that's actually a perfect square trinomial. That thing right there factors into x plus 5 times x plus 5. And finally, down here in the denominator, you might be thinking, how do I factor this? It's not a quadratic. You're not going to create this into two binomials. But what I can do is factor out the common factor of 2, which I'll do to get 2 times x minus 3. All right, now I've set this up to apply this same technique. What I'm going to do before I multiply things together is just cancel any common factors between the numerator and the denominator one for one. Here I have an x plus 5 and an x plus 5. I can cancel those out. There's an x minus 3 in both the numerator and the denominator. And then this x plus 3 in the numerator and denominator over there. After I've canceled all of those factors, I'm just going to see what I have multiplying across in my numerator and denominator. And it looks like I just have this x plus 5 left in the numerator and this 2 in the denominator. That there is my fully simplified expression for the multiplication of these two gnarly rational expressions. And again, it was fairly simple outside of the factoring, which does take some time, and you got to get good at that to be good with these. But once I've factored them, I'm just canceling one for one any common factors. I just want to make a quick note of that. There were two factors of x plus 5 in the numerator over here, but there was only one down here. With that one can only cancel one of those. That's an important thought. And it doesn't matter if you're in the same numerator and denominator or opposing. Any numerator factor and any denominator factor can cancel out. Once I'm done, I multiply straight across. Let's now look at addition of rational expressions. All right, here we are with our final example in this video. We're going to add two rational expressions together. Again, we're just going to employ the whole idea with fractions, which is you need to have a common denominator before you can add two fractions together. The same thing here. The only way that we can build fractions to the same denominators, as with normal fractions with numbers, is that what we need to do is multiply one or both of these denominators by something that will make them the same. Okay, but remember now, we have these fractions, but what we have going on are polynomial operations in the numerator and the denominator. So the game is, what do I need to multiply in this case, this fraction by, or this rational expression, so that in the top and the bottom, a factor of 1, so that it has the same denominator as this one right here. I'm going to show you what I would need to do that, and then I'll backtrack and tell you how I figured that out. What I'm going to do is multiply this expression by a factor of 1, that is x plus 7 times x plus 7. I'm doing this because of what's going to happen in the denominator. Now again, remember, when I multiply these, it's polynomial operations. Down here in the denominator, I'm going to need to FOIL these together, or just use polynomial multiplication. And up in the top, I'm going to be using distribution to put them together. So let's do that multiplication. Down here in this, what I'm going to end up with, I won't show all the operations, but it ends up at x squared plus 13x plus 42. And in the numerator, I'm distributing to get x squared plus 7x. And then I have this expression still hanging out over here, waiting to join the party. All right, so as was the plan, when I multiplied the numerator and denominator by x plus 7, I changed this denominator from an x plus 6 into an x squared plus 13x plus 42. Now it's exactly the same as the other rational expression. Let's stop for a second and be, how the heck did I know that multiplying that by x plus 7 would make it to be exactly the same polynomials on the right-hand side? Well, I simply factored this previously, so I hadn't shown this, but what I did previously was I factored this quadratic into an x plus 6 times an x plus 7. What that means is that polynomial is simply, if I think about it as a multiplication of binomials, it's this x plus 6 times x plus 7. Over here, I already had the x plus 6, so I'm realizing all I need to do is multiply this by x plus 7, and I will result in the same polynomial expression. Whenever I'm doing this, what I'd want to do is factor each of my denominators and then look how can I build them into that same common denominator. It's something that we can do with numbers also using prime factorization or whatnot. But there we go. We have our common denominator. That was the tough work. Now what we do is we're going to add these two fractions together. As always, we keep this common denominator. We're going to add the numerators together. Again, it's all within the lens of polynomials. This plus this expression would give me an x squared, and the 7x plus 3 more x's would give me 10x, and then the 24 is the only constant coefficient. So congratulations, if that made sense to you, you understand how to add gnarly rational expressions together. Though before we're done, every single time we're dealing with rational expressions, we need to make sure we're as simplified as possible, right? Again, we're adding and simplifying. So what I'm going to do is I'm always going to take this, I'm going to factor the numerator and denominator just to check to see if there's any common factors between the numerator and the denominator. I already know this denominator factors into x plus 6 times x plus 7. The numerator there would factor into an x plus 4 times x plus 6. Lo and behold, we do have a common factor. We have a common factor of this x plus 6, which we can cancel out, leaving us with the expression x plus 4 over x plus 7. That ties everything together for rational expressions. The only concepts we really haven't tackled are excluded values, domain issues around rational expressions, and then rational equations, but those will be covered in a new video.